Welcome everyone to this video on the chapter of circular motion. So today we'll be studying the topic of angular velocity. So when we talk about angular velocity or instantaneous angular velocity, we can take some ideas from what we studied in the chapter of kinematics. So in kinematics we studied that as a body is moving from one point to another, then its velocity changes from instant to instant. So we define two different types of velocity, that is average velocity, which shows the overall change in the displacement or the distance covered by the particle per unit time, and the instantaneous velocity. So in the same way we define the idea of instantaneous angular velocity of the particle. So let us take the case of the car which is traveling in a circle from this point A to B, and it has covered some angle d theta. So it has covered some angle d theta in some time interval dt, some small dt time interval it has covered this angle. So it defined instantaneous angular velocity as the ratio of the small angle covered divided by the time interval taken. So to compare this with the average angular velocity, in the last question which we did, the particle went from point A to B in the time of 5 minutes, and it covered an angle, as you can see, of pi by 2 radians. So the average angular velocity of the particle between points A and B was pi by 10 radians per minute, whereas we can judge that the car may or may not have traveled with this angular velocity throughout its motion. At the starting of the motion, it may have traveled with some lower angular velocities, and at the end of the motion, it may be traveling at some higher angular velocities. So, its angular velocity at a particular instant, that is the ratio of the angle covered in small interval of time, would be changing with time, but the overall angular velocity was this. So that's why a need is born out to define the value of angular velocity, which is defined as d theta by dt. We define this also in the way that it is defined as the limit in which the time interval approaches zero for the ratio of the small angular displacement of the particle and the time interval. So this is also the definition of angular velocity, and this whole limit expression changes to d theta by dt. Now angular velocity also has direction, just like average angular velocity. For average angular velocity we define anti-clockwise and clockwise, and in those sense we take positive and negative direction. Same thing we say for angular velocity, that for anti-clockwise motion of the body it is positive, for clockwise motion it can be negative, and it's just a sign convention, it can be taken opposite sense also. So let us move on to the example. So in the first example, we have the angular position of particle going in a circle. It is given by the law this. So we are given the angular position of the particle theta. So theta is equal to theta naught sine A into t. So this is the angular position of the particle, and theta naught is some constant, and as the particle starts moving from t equal to 0, it would start moving from some 0 angle towards this angle theta naught. This is what we can judge from this particular value. So in the first part of the question, let us read what is asked in the question. So it is asked in the question, find the average angular velocity of the particle between t equal to 0 and the first time the particle reaches the angular amplitude, that is the maximum angular displacement. So the time at which the particle would reach the angular amplitude, that is the value theta naught, would be when sine at becomes 1, that is the value at becomes equal to pi by 2. So this implies that the value of time should be equal to pi by 2. So this is the total time taken by the particle in going from point 0 to point B, and we would say that the average angular velocity of the particle in going from point A to point B, or from point A to from a zero angle to the maximum angular displacement, would be the angular displacement of the particle, that is theta naught, divided by the time taken by the particle in covering that angular displacement, that is pi by 2a. So we'd say that the average angular velocity of the particle would be the value of 2 theta naught into a divided by pi. So this would be the average value of angular velocity. After that, we would say that what is the angular velocity of the particle at t time. So the angular velocity of the particle at t time can be evaluated using the formula which we just defined. So differentiating the angular position of the particle theta naught sine 80. The omega is equal to theta naught into a cos 80. So this would be the instantaneous angular velocity of the particle. Let us do question number 1. A particle is angular velocity of the particle is given by omega 2 e की power 3t radians per second. Find the angular displacement of the particle in t time. So we can easily say that omega can be written as d theta by dt, that is equal to 2 e की power 3t. Angular displacement d theta is equal to 2 e की power 3t into dt, and then we'll integrate this particular value from some value 0 to theta, and the RHS of the expression to some t time. So we'd say the complete angular displacement of the particle in time t can be written as 2 by 3 e की power 3t, and the limits going from 0 to t. So this would easily come out to the value theta is equal to 2 by 3 e की power 3t minus 1. So this would be the value of angular displacement of the particle in t time. Next, let us do the topic of average and instantaneous angular acceleration. Again, the same story goes that we'll be defining average angular acceleration same as we defined average angular velocity. So the symbol for angular acceleration is this alpha, uh, and average angular acceleration is defined as the final angular velocity of the particle minus the initial angular velocity of the particle divided by the time interval delta t. So in the same vein, we can say that what would be the value of instantaneous angular velocity. So the value of instantaneous angular acceleration, acceleration will be meaning what is the value of instantaneous angular acceleration. So we would say it would be the limit in which the time interval approaches 0 for the average angular acceleration. That is, we are calculating the value of average angular acceleration only. It's just that the time interval is approaching very small values. So final angular velocity of the particle minus initial angular velocity of the particle can be written as delta omega, and the numerator would remain as it is. So angular acceleration of the particle can be written as d theta by dt. That is the small d omega by dt. That is the small change in angular velocity of the particle in some dt time interval that should give us the angular acceleration of the particle. So this expression shows the instantaneous angular acceleration of the particle. And this expression shows the average angular acceleration of the particle. So let us take an example. A particle goes in a circle with angular acceleration of 5 degree per meter square. Convert it into SI unit. So we have to convert 5 degree per minute square into SI units. So 5 degree can be converted into pi by 180 radians and minute square. So 1 minute can be written as 60 seconds, and we can square this value. So this would come out to be pi by 36 into 1 by 3600 radians per second square, or this can be written as pi by 360 squared radian per second square. So we converted 1 minute into seconds value and 1 degree into radians value, and we were able to convert angular acceleration to its SI unit. And by this exercise we were able to determine the SI unit of angular acceleration also. Now let us do the question. The angular displacement of the particle as a function of time is given as at minus bt square. Find the angular acceleration of the particle with respect to time. So we are given the value of angular displacement of the particle with respect to time, which is at minus bt square. We are supposed to find what is the angular acceleration of the particle at some instant. So we know that d theta by dt, this gives us the angular velocity of the particle. So differentiating this expression once, you would get a minus 2bt, and then differentiating the value of omega again, you would get 0 minus 2b. So that means the angular acceleration of the particle following this particular law would be minus 2b. Let us take an example. A car going forward is speeding up. The wheels of the car demonstrate angular acceleration. A stone tied to a thread whirled in a circle when it is whirled with increasing angular speed. It also demonstrates angular acceleration. So those were some examples of angular acceleration actually. That what are some examples of angular acceleration? Like when the car is going forward and it is speeding up, so its wheels are having some angular acceleration, and when a stone is tied to a thread and it is whirled in a circle, then it also shows a sign of angular acceleration. Two particles are going in a circle as shown with angular acceleration alpha 1 and alpha 2 respectively at a given time. So it is known that angular acceleration at some time is more than the angular acceleration at some other time. So we are given some figure, let us draw it. So in this figure there is a circle, and it is given that the angular position of the particles are some theta 1 and theta 2 points at our P1 and P2. So it is given that angular acceleration at the point number 1 is greater than angular acceleration at point number 2. That is alpha 1 is greater than alpha 2, and as the figure suggests, theta 2 is greater than theta 1. the question asks us that can we find a relation between omega 1 and omega 2, that would the angular velocity at 1 would be greater than angular velocity at 2, would the instantaneous angular velocity at 1 be less than at 1 at omega 2, or would they be equal? So the correct answer is we are not given sufficient information to determine the angular velocities at these 2 points. We are given angular acceleration, we are given angular position, but we do not know about angular velocities. So angular velocity can show us the rate of change of angular position, but not the angular position. Similarly, angular acceleration can show us change in rate of change of angular velocity, but cannot show us angular velocity itself. So this was a rather easy question. Relation between linear and angular variables. So we know that as a particle goes in a circle, it subtends an angle theta, and the angle subtended by the particle is given by the ratio of the length of the arc and the radius of the circle. So we say that the angular displacement of the particle is some L by r, or we can say the linear distance traveled by the particle is equal to r theta. So let's say if the particle is traveling some small distance dl, so it would travel by a small angular displacement d theta. So in that case we can say that r d theta would be equal to some small angular displacement, some small linear displacement dl. That is what we want to say, is that if this becomes d theta, this would become a small linear displacement dl. For our current use, uh, yeah, now what we can do is that we can divide this value by dt. So we can say dl upon dt is equal to r d theta by dt. Distance covered by the particle per unit time is the speed of the particle, and we know that d theta by dt is omega. So this comes to show us a relation which can be used pretty often, that v is equal to r omega. So this is a common relation which has been in use, and we'll be using it in this chapter. Now what we can do is that we can differentiate it even further, and after differentiating the expression of velocity, we would get the acceleration of the particle, and by differentiating the angular velocity of the particle, we would get angular acceleration of the particle. So this expression, this acceleration of the particle is actually the linear acceleration of the particle, and this can be sometimes called the tangential acceleration of the particle. So after differentiating velocity, we'll get linear acceleration, and after differentiating angular velocity, we'll get angular acceleration. So now let us take some analogous equations, talk about some analogous equations. So we already know that angular velocity of the particle is equal to d omega by dt. Let us take a case if alpha is a constant and the angular velocity of the particle is going from value omega naught to omega. So omega naught is the initial angular velocity of the particle, and omega is the final angular velocity of the particle. So after putting d omega and alpha by dt, that is writing the expression like this, and putting the sign of integral, that is the angular velocity is changing from omega naught to omega and the time changes from 0 to t, we can write an equation that the angular velocity of the particle after t time is equal to the initial angular velocity of the particle plus alpha into t, which is the equivalent of the equation v is equal to u plus at. In the same way, we can write more analogous equations, and they can be derived in the same way also, just like we derived this one. We already know the equation, or more equations of motion, like x is equal to ut plus half at square. So these equations are from kinematics, right? So as these equations are analogous, we can also write similar analogous equations, that the angular displacement of the particle, that is theta minus theta naught, would be the initial angular velocity of the particle omega naught t plus half angular acceleration into t square. Same way we can write omega square is equal to omega naught square plus 2 times angular acceleration into some angular displacement delta theta. So these equations can be used in solving questions which have a constant angular accelerations and which demand us in evaluating in terms of angular variables only. That is, if you are given alpha and you are given initial angular velocity, what would be the velocity of the particle after t time and such. So let us do a question on this idea. A particle goes in a circle of radius r equal to 5 meters. The initial angular speed of the particle is given as 1. The particle has an angular acceleration of 2 radians per second square. We have to find the angular speed and the angular displacement of the particle at 5 seconds. So what would be the angular speed of the particle when 5 seconds have gone by? So it's the equation initial angular velocity plus angular acceleration into time would give us final angular velocity. Initial angular velocity is 1, angular acceleration is 2, time taken by the particle is 5 seconds. So this should give us 11 radians per second. So this would be the final angular velocity of the particle, and the angular displacement of the particle would be 1 into time taken by the particle, that is 5 seconds, plus half of angular acceleration of the particle, that is 2 into the time taken by the particle, 5 squares. So this should give us 5 plus 25, that would be equal to some 30 radians. That should give us the angular displacement of the particle in 5 seconds. So we'll be ending this particular lecture with this question. In the next lecture, we'll be starting with the idea of centripetal and tangential accelerations. So thank you for joining and have a nice day.